Hey everyone, this is the solution set for the quiz from last Monday, July 6th, and what is actually just the first quiz in the course. Let me get my camera wire out of there. Alright, so number one. We have two charged metal balls that are 3 centimeters apart, and they have identical charges of plus 2 microcoulombs. So let's just sketch this. Oops. Okay, so remember, for our purposes of calculating, we generally want to have things in units of SI quantities. SI quantity for electric charge is the coulomb. So before we do any calculations, just like we did last term when we usually converted centimeters into meters or grams into kilograms for the purposes of calculation, we want to convert microcoulombs into just plain coulombs, just like we're going to do by converting centimeters into meters. All right, so the electrostatic force between them can be found just from Coulomb's law. So that's pretty straightforward to plug in. We have our electrostatic constant, 8.99 times 10 to the 9 Newton meters squared per coulomb squared. And then we'll multiply that by the product of our charges divided by the distance between them. In this case, Q1 equals Q2, so we'll just throw that in there and we'll square it. And then we divide by our distance. All right, and carrying that multiplication out, you should find that the force between them is going to be about 40 newtons. All right, for part B, we're given a force, and the distance is the same, but we want to find Q. So assuming that the charge on the two balls is the same, then the force between them is just going to be, as it was before, Ke Q squared over R squared. Oops, let me move that up. And we need to solve for Q. So solving for Q gives us, let's see, we take a square root, we get F R squared over Ke. Alright, it looks like I'm running out of room on this page, so I'll just quickly move to the next one. And we get, square root is, we know our force is 20 newtons. We know the distance is still 3 centimeters, or 0.300 meters. Sorry, 0.0300 meters. And now we divide by our electrostatic constant. And thus we figure out that the charge on each ball is now actually reduced to 1.41 times 10 to the minus 6 coulombs, or 1.41 microcoulombs. So that's number one. All right, number two. So we have another charged sphere. And this sphere has a charge of 15 microcoulombs, which you could also write as 15 times 10 to the minus 6 coulombs. and we place a test charge of -5 microcoulombs away from it. We'll call this Q prime, or Q naught. And the distance between the two, draw a slightly better line than that, is 50 centimeters. And the angle it makes to the positive x-axis, which is important for the purposes of figuring out the components, is 60 degrees. Alright, so for part A, the magnitude of the electric field is pretty straightforward. We know that the electric field of a point charge, or of the charged ball, which we'll treat as a point charge, is just going to be Ke Q over R squared. So the magnitude of the electric field at that point, where the test charge is going to be 5.39 times 10 to the 5th newtons per coulomb, which is one of our units of electric field. The other unit of electric field, as we found when we started talking about capacitance, is the volt per meter. So that's part A, pretty straightforward. Now for part B, we want to figure out the components of the electric field at the point where the test charge is placed. So, vector components haven't changed since General Physics 1. They still remain the same. Our vector components go like this. So the x component of the electric field is just going to be the magnitude of the electric field times the cosine of the angle. And the y component of the electric field at that point is going to be the electric field at that point times the sine of the angle. So then Ex is just going to be that 5.39 times 10 to the 5th newtons per coulomb times the cosine of 60 which gives us an electric field of 2.70 times 10 to the 5th newtons per coulomb in the x direction. And the y component is going to be that 5.39 times 10 to the 5th newtons per coulomb again, times the sine of 60. And that gives us a y component of the field to be 4.67 times 10 to the 5th newtons per coulomb. So those are the components of the electric field at the location of the test charge. Note we haven't put the test charge there yet. We're just interested in finding what the value of the electric field is at that point when we put it there. So in part C, that's when we actually put it there, and we want to figure out the magnitude of the electric force on the test charge. So we know that when you place a charged particle in a magnetic field, or I'm sorry, in an electric field, it feels a force equal to the charge of that particle, in this case Q naught, times the magnitude of the field at that point. So we already have the magnitude of the field at that point. So we just need to multiply by the charge on the test charge. So let's see, our test charge is -5 microcoulombs. And the value of the field at that point we already found to be 5.39 times 10 to the 5th newtons per coulomb. So the force it's going to feel is negative 2.7 times 10, or just negative 2.7 newtons. And an interesting thing to note when we talk about electric forces is that the sign on the magnitude of the force tells you whether the force is attractive or repulsive. Since the sign of the force is negative, the force will be attractive, which makes sense because our test particle has a negative charge, but our charged metal ball has a positive charge. So we know that opposite charges attract each other, so we expect if we release this system from rest, they'll move together. On that topic, electrostatics can be kind of an artificial setup. It works well for slow-moving systems that don't evolve rapidly, but it is a little bit artificial in that we're somehow holding these charges in place without releasing them and letting them slam together or fly apart as they actually would in the real world.